subtract, or if you want, you can appeal to the mean value theorem. This is equal to f prime at some point v, where v lies between t and t plus h. By the mean value theorem. Okay. So what is f prime of v? Okay. I can differentiate this first. So I get 1 over 2 pi log v over 2 pi. And then I differentiate this next. So I get v over 2 pi. And now the derivative of the log is 1 over v over 2 pi. And then a 1 over 2 pi. So this is a minus 1 over 2 pi. So this part, did I do this correctly? T over v over 2 pi, 1 over t over v over, oh, this whole thing cancels. That's fine. This v over 2 pi cancels this one, and that cancels that. So you actually end up getting this, which is asymptotic to 1 over 2 pi log t. So the contribution due to this factor, even in a small box, can be estimated asymptotically to be about log t. But the problem is, we'd have poor information about the change in the argument of zeta of half plus it. So combined with 1, this is corollary 1. Now, let me just make one comment here. So there's just a remark. We won't get to this yet. The argument of zeta half plus it, which is one of the things that dominated our discussion in the proof of this theorem, this is denoted by S of t. And Selberg in particular, the great Atlas Selberg, had investigated S of t and observed a sort of a Gaussian distribution of values of S of t on the half line. Okay? And some recent improvements of Selberg's result are by this very young mathematician Radziwill, who is getting the Shastra Ramanujan Prize. Not for that work, but he's getting it for other work. But he did that as part of his thesis work in Stanford, Colorado. So ST is very much in discussion even today in terms of research. Okay, so this is quite an intriguing function to study. Really, and it's quite central in the distribution of prime numbers. So let's look at corollary 2. Corollary 2 says, if we write the zeros in the rectangle, in the critical rectangle which I've written, as beta n plus I gamma n, then this imaginary part gamma n is asymptotic to n over 2 pi log n. So there are about t log t zeros up to t. So the height of the zero will be of the order of magnitude. So this is sort of the opposite of the prime numbers. I want you to notice this. The number of prime numbers up to x is about x over log x. So the nth prime number is like x log x. Here the number of zeros up to t is like t log t with a constant. So the height of the nth zero is n over log n. Okay. All right, so let's quickly confirm this. So just observe that n of gamma n minus 1, we are going into a rectangle of height gamma n minus 1, and definitely that's smaller than n. But if I go to a rectangle of height gamma n plus 1, I definitely have all the zeros up to height gamma n. But this one, by corollary 1, is less than or equal to n of gamma n minus 1 plus capital O of log of gamma n by corollary 1. So that's why I stated corollary 1 in this form. The gap between that is of the order of magnitude of the log. Therefore, the gap between that and that is the order of magnitude of the log of gamma n. All right. So, what can we say about gamma n? Therefore, gamma n is now asymptotic to, so you can say gamma n log gamma n, right, is now asymptotic to n. If we apply the Riemann von Humboldt formula, because I know, so n is squeezed between these two, so we can flip over. This is capital O, and this is of that size. Therefore, gamma n log of gamma n is asymptotic. Now, that is the same as saying gamma n log gamma n is asymptotic to 2 pi n. Okay. All right. Now, this means that gamma n is less than or equal to n for large n. And gamma n is greater or equal to n over log squared n for large n, right? Because gamma n cannot be of the size of n, because then I would go beyond. Gamma n cannot be smaller than n over log squared n, because I am multiplied only by log and I will not reach this height, which implies that log gamma n is asymptotic to log n. And therefore, from 3, we get that gamma n is asymptotic to n over log n. I think I should put a 2 pi here, right? Times 2 pi. I will do by the numerator. From 3. Okay, which is corollary 2. Very good. So, corollary 3, the sum of the reciprocals of the gamma n's for n less than or equal to x is asymptotic to 1 over 4 pi log squared of x. This is obvious. And the sum of the reciprocals of the gamma n is asymptotic to the sum of the reciprocal to 1 over 2 pi log n over n. And that's asymptotic. Okay. So this is sort of some general things, but now we will get into things a little bit more specific. We'll look at the growth of the C function as an entire function and appeal to the theory of entire functions and the distribution of zeros to write a product representation for the C function in terms of the zeros. And this will, of course, lead to a product representation for the Riemann zeta function. That's not quite correct. It's s minus 1 zeta s in terms of the zeros. And we can also get a series representation for zeta prime of s over zeta s in terms of zeros. And all this is connected to, so to speak, an exact formula from psi of x where we can write it in terms of the zeros of the Riemann zeta function. Okay, so this is sort of the direction in which we are going. All right, so now we're going to talk about the order of an entire function. So I have not had an occasion to talk to Professor Li Shen, who generally does this. Others who do this course on complex variables. I'm not talking about the 4,000 pi problem, I'm talking about the 6,000 complex variables. But how many of you had the 6,000 complex variables? So do you cover orders of magnitude of entire functions and the Hadamard-Weierstrass theory then?
We did the Weierstrass product formula.
In the second group.
Yeah, in the second.
So I'll just quickly recall, going through whatever is needed for our purpose here. But that's in the second semester, right? Yeah. Because the first semester is typically what is needed for the qualifying exam, right? And you basically do Cauchy theorem, residues, and maybe Romeo's theorem, and a little bit of, I forget it. It's a long time since I taught that course. So I don't know if things have changed. But the point is this. Now this is not mandatory to take the complex variable exam, right? I mean, you choose real variables, you can skip one, which personally I don't like. But students are given your choice. It's a little bit simpler in terms of qualifying exams. Okay, so the order of an entire function is, so let f of z be an entire function. And, okay, we say f is of order omega. Now, omega could be infinity. Omega could be 0. We're going to see what omega is there. But this is defined. Omega is the lim sup as r tends to infinity log mr divided by log r. So this is a definition where m of r is the sup on absolute z equal to r, which is the same as saying absolute z less than or equal to r by the maximum modulus principle of absolute value of f. So this is the size of the function f on a circle, on a large circle of radius r. So you take the biggest value of this, which is the biggest value of the circle, and you're going to take the log of that and compare it with log r. So what does this mean? Let's write this in a more meaningful form, okay? Equivalently, the reason we write it this way is that this is always defined, and this could be infinity. But this other way in which I'm writing, it may not be defined, especially if you have got an infinite exponent. Okay. So equivalently, your m of r lies between e to the r times 1 plus epsilon. So it grows e to the omega. Sorry. Right? M of r is e to the r to the omega times 1 plus epsilon. Log. It's no faster than that, but m of r grows faster than e to the r to the omega times 1 minus epsilon. So that's what it means. It's a double exponent. So when you say you have an entire function of order 2, it grows no faster than e to the r to the 2 plus epsilon, but it definitely grows faster, the m of r grows faster than e to the r to the 2 minus epsilon. So that's what the order of an entire function is. So, but in this form, it's not clear that omega is could be infinity. It makes no sense. So this makes better sense with omega infinity, but this makes sense with omega finite. So what we should say is equivalently, if omega is finite, then this makes sense. And could be 0. Okay. So you can also have an entire function of order 0. So omega finite means we call it an entire function of finite order. Okay. So having said that, let us look at the order of the C function. So what is the order of the C function? Okay. So theorem, C of S is entire of order 1. So that means you have to only do 1 plus epsilon, 1 minus epsilon. That's what it means in terms of order. So C of S is an entire function of order 1. So proof. So first of all, C of S is C of 1 minus S. We focus on real part S greater than or equal to half. Now the advantage of focusing on real part S greater than or equal to half is I can use the Stirling approximation for the gamma factor of C of S, and I can appeal to an upper bound for the Riemann zeta function in the half plane greater than or equal to half, which also we obtained. So we immediately will get an upper bound for the C function on a circle of radius r, which will give something like this, and we have to get a lower bound. Okay. Thus, for real S greater than or equal to half, the absolute value of C of S is less than or equal to pi to the minus S over 2. That's just pi, that's of no consequence. Gamma S over 2, right? But gamma S over 2 is, well, we'll put that, zeta S. So this is capital O, or gamma S over 2 by Stirling's approximation is e to the power, the logarithm of this is e to the power S over 2 log S over 2, right? So I'll put the absolute value. Minus S over 2, but you know, if you want to, but you don't know about the minus. I mean, it's absolute value, so we'll put that. So that is for the gamma factor. And what about the zeta function? The zeta function is absolute value of t to the power 1/2, which is absolute value of S to the power 1/2. Now that gets absorbed in the log, actually, S over 2 gamma S over 2 plus capital log exactly that's exponential, that's absorbed there. So this is of order of magnitude. That means the MC of R, right, is of order of magnitude no more than e to the power R over 2 log R over 2 plus R, something like this. And that implies that is capital with e to the R plus epsilon. Now what about the lower bound? Well, m of R is the supremum of the function on the entire circle. So for the lower bound, all I will do is to calculate exactly the value for the real positive number R. Okay. So this is equation 5. To get a lower bound for m of R, simply note that m of R is greater than or equal to the value of the C function at the point R. And the value of the C function at the point R is pi to the minus R over 2, gamma R over 2, zeta R. But now as R is going to infinity, zeta R is going to 1. this is only decreasing as a function of r. So, but it does not decrease as fast as this increases. This is a factorial. So this is equal to e to the power r over 2 log r over 2 minus a quantity which is of the order of magnitude of r. Positive. And therefore, this is greater or equal to e to the power r 1 minus epsilon. In fact, it is this. So to speak, we actually have an asymptotic estimate of the logarithm exponent, right? Hence, omega is 1. So the C function is an entire function of order 1. All right, so the next thing that we look at is the exponent of convergence of the roots of the function. But I'm going to state here a general principle, because we can use this for other entire functions. But for the C function, we already know the answer because we know the roots of the C function, and those are your beta plus I gamma within the strip. But I'm going to put this in the context of a general result, which you will find useful. And so this comes out of something called Jensen's formula. So it's a good exercise to go through. It's not very difficult, but it's instructive to go through it. Okay, so anyway, we talk about exponent of convergence. Of the roots of the entire function. By the way, when we talk about roots of the entire function, we can actually take any entire function and solve f of z equal to any complex number z0 that you like. That is simply the roots of f of z minus f of z0 equal to 0. So whatever I say here applies not just to f of z equal to 0, but for the values that you get by solving f of z equal to z0 for any z0. Right? Because I look at the difference, I have an entire function. So we now introduce what is called the exponent of convergence. All right. So let f of z be entire. And let z1, z2, zn, be its roots. Written in ascending order of absolute value. Now this could be a null set. E to the z is entire, so there are no zeros. Okay. So written in ascending order of its absolute value. So we have absolute z1 less than or equal to absolute z2 less than or equal to absolute z3 and so on. Roots can be multiply, occur with multiplicity, then you write them as often as you want. But one thing is clear, that there are no more than a finite number of roots on a given circle, because if you had an infinite number of roots on a given circle, they will cluster. And the roots have to be separated, because otherwise they will again cluster. So the only limit points of the roots, if any, would be at infinity. So only limit point is infinity. So that's the only limit point of the roots. So now I define the exponent of convergence. The exponent of convergence of Zn, denoted by mu, is defined as mu equals the lim-inf of all exponents lim-inf of the set of mu such that summation 1 over Zn mu is less than infinity. So take all possible exponents for which the sum of the reciprocals will converge, and take the inf of all that, and that is called the exponent of convergence of these roots. So now we have a theorem. Okay? And the theorem is that the exponent of convergence is always no bigger than the order of magnitude of the order of the entire function. Okay, so that's the theorem. We'll actually prove this theorem. This is true in general. But here, what we are going to say is we know the exact exponent of convergence, and this is just a verification. So we'll just do a verification here for C. So in the case of C, omega is 1. But in the case of C, we actually know this sum of the reciprocals. That behaves, each gamma behaves like n over log n. So 1 over gamma is like log n over n. So if I do 1 plus epsilon, I will get convergence. But nothing less than 1 plus epsilon will give me convergence, because at 1 I get divergence. Therefore mu is 1 in this case. So by corollary, so omega equal to 1 by theorem 1. By corollary is 1 and 2. Mu is 1. So this is verified, just in this case. Right? But let us prove this more generally, because we can use this for other functions. Yes?
When you write the lim in, is that just an inf? Because I'm not seeing what are the...
Yeah, it is the inf.
Okay.
I wrote lim in. It's really thank you. The inf for this. We don't need the lim. All right, so now let us actually prove that the exponent of convergence is less than or equal to omega in general. Okay, so this, for those of you who have not seen Jensen's formula of an application, we'll just do it very quickly. And that will be useful for me to set up the Hadamard factorization theorem, because this is related to that. Okay. So let's look at Jensen's formula. So I'm just going to say recall. That means for those who have had that complex variable. Okay. So recall Jensen's formula, which we will prove. So what is Jensen's formula? It's the most of 1988. Okay. And I actually gave a summer course on the Riemann zeta function in Dirichlet series in 1988. And those were the days when the department had enough money that they would invite faculty members to give lots of topics courses. So graduate students, not just in math, but from computer science and physics, would take these graduate courses. So I gave one time a graduate course on the Riemann zeta function, another time a topics course on Silk methods and so on. And they were always well populated. And then afterwards, it all became individual study and so on and so forth. And I don't like that trend. I mean, you know. All right, so anyway, so Jensen's formula. So let F be analytic. In absolute C less than or equal to R. F of 0 not equal to 0. And let Z1, Z2, Zn be all the zeros of F in absolute Z less than R. Okay. Maybe I should also say that F of R, there is no 0 on R. Anyway, multiple zeros written multiply. All right, then the claim is that 1 over 2 pi integral 0 to 2 pi of the logarithm of the absolute value of f of r e to the I theta d theta minus is equal minus log f of 0 equal to the logarithm of r to the n over the product of the roots. That's the Jensen's formula. Okay, so you might wonder what happens if there is a 0 on R. Well, one thing we can do is we can choose a radius on which there is no 0, because the zeros have to be isolated. Okay, so we can always choose within that a skin of the circle where there is no 0 and apply Jensen's formula there. Also, the rate at which the logarithm goes to infinity does not really affect the convergence of the integral. So for example, integral dt over t, as t goes to 0, diverges, that part. But dt over square root of t does not diverge. Similarly, log t will not diverge, log t dt, even as t goes to 0. Even though log goes to infinity, the area still remains finite. And so the same principle will apply here. Okay, but we don't have to get into that technicality. If you're worried about it, just to choose a circle R on which there are no zeros, and then apply Jensen's theorem. Okay, so proof. No, but this is something to be taken into account if you are concerned about the actual logarithm proof. Okay, so proof. So let you write f of z as z minus z1, z minus z2, z minus zn times capital F of z. Okay. So write it that way. So F is analytic in absolute Z less than or equal to R and 0 free. So it's an analytic function which is 0 free. Okay? So note that, because I've written that way, the absolute value of f of 0 is the product of the roots times f of 0. Okay, you also have that. So now, the theorem is therefore equivalent to the following. That is Jensen's formula. So Jensen's formula is equivalent to, and this is what I'm going to do. We're going to replace the little f by this product involving the capital F and this, and use the fact that this is 0 free. Okay? So this is equivalent to summation j from 1 to n of 1 over 2 pi, the integral from 0 to 2 pi, of the logarithm of r e to the I theta minus zj, right? So that's